Good morning. Today will be the last class of new material. And let me make it a little less loud and feedbacky. Today will be the last class of new material before the final exam. There might be some material that we will not get to today that we'll cover in the first part of Friday, but the rest of Friday will be a wrap-up of the entire course and what are the main take-home messages and what do I hope that you take with you onto your next classes in the curriculum. So today's lecture I'm titling Mop-Up Duty. So there are some topics that are on the course description on the registrar's website that we did not get to until today, but we will get to today relatively directly. And it's kind of a fun topic. It's the scaling laws. Why do what nanoscale phenomena arise not because of quantum confinement and plasmonics and electronic transitions and electron plasmas and van der Waals forces at small scales, but just based on the fact that something is small, just based on the fact that its surface area goes up a lot faster within a small object than with a big object. So a flea has a much larger surface area to volume ratio than an elephant does, and it also has a higher strength to weight ratio. And all of these continuum phenomena that don't rely on quantum mechanics or any knowledge of chemistry or the granularity of matter, but are still nonetheless true. So this is the topic of chapter 2 in the book, which I would encourage you to read. It's a very short chapter. We're going to cover about a third of it, but the rest of it is interesting as well. Also, your homework, all 4 homework problems this week are from the book. The solutions are already posted. 3 of them are from chapter 2, and 1 of them is from chapter 4, but it's a related topic. Okay, so scaling laws are crude rules of thumb that are not real laws in the sense that F equals ma or the Schrödinger equation are real laws. They're just sort of ideas to guide the mind, because we use a lot of engineering assumptions in our discussion of scaling laws. So let's say we have some object with rectangular cross sections in every dimension, and we have height, width, and the last one, length. And we know that the volume, length times width times height, is proportional to d cubed, and d is some characteristic dimension. Some characteristic dimension or size. And it's along D is along one axis, so for a hydrogen atom, what would be its characteristic size? Any atom in units of meters, or something that's derivable from meters. 10 to the minus 10 angstroms, so 10 to the minus 10 meters, or 1 angstrom would be the characteristic size. Characteristic size of an elephant might be 1 meter. Maybe the characteristic size of a human would be half a meter if you take kind of an average of our length, width, and height. But the surface area the surface area equals 2 times the length times the width plus the length times the height plus the height times the width, or 2 times d squared plus d squared plus d squared, or proportional to d squared. So the ratio of surface area to volume is proportional. That's what this fish symbol looks like, is proportional to. I have other drawings of animals in this lecture too. One more compelling than the last. Each more compelling than the last. Proportional to d squared over d cubed, or proportional, in other words, to 1 over d. So if we have a this is a personal challenge to myself. He's smiling, or she. This is an elephant and this is a flea. As if you couldn't tell by my impression of an elephant. Characteristic size of an elephant, 1 meter. Characteristic size of a flea is 1 millimeter. Surface area to volume ratio, 1 per meter, and the surface area to volume ratio for a flea is 1,000 per meter. Means that if you take the surface area to volume ratio per meter and you multiply it times the volume, you get 1,000 times bigger surface area for the flea than you do for the elephant. Okay, so far, so good. This, by the way, has consequences in the efficiency with which the elephant and the flea can dissipate heat energy to the outside world. For example, an elephant has to be much more efficient in its metabolism because it doesn't have as much surface area to dissipate the heat generated by biochemical processes. This has consequences in strength to weight ratios as well. And this is quite fine-grained from the animal kingdom all the way to Olympic weightlifters, because the strength of a muscle, for example, of a muscle is proportional to the cross-sectional area which is proportional to the characteristic dimension or size squared, but the weight is proportional to the volume, which is proportional to d cubed. So the strength to weight ratio is also proportional to 1 over d. So for the elephant, that is 1 per square meter, and for the flea, that is 1,000, or sorry, 1 per meter. I might have said square meter. I don't mean that. 1 per meter, and the elephant, 1,000 per meter. So this means that if if a flea can support 100 times its body weight, which is approximately correct, then an elephant can only support 1/10 its body weight. Now you can imagine a flea supporting 100 other fleas, and you've even seen ants carrying around like giant leaves and dead spiders and all kinds of crap. But imagine watching an elephant carry 10 other elephants. Imagine the two of these creatures falling out a 2-story window. Or imagine them falling off the Empire State Building. The flea will most likely survive that mechanical insult. The elephant, I will not finish that sentence or thought. Oh, it's too late. What about Olympic weightlifters? This is right out of your book, but it's a kind of a cool example. We're going to plot the percent of body weight lifted and plot it against the weight class in kilograms of the athlete from 410 to 530%. And what we find is that there is, believe it or not, and this was the 2004 Athens Olympic Games. There was exactly a linear relationship. Pretty incredible. One of the questions that I did not assign, but is in the back at the end of the chapter, end of chapter 2 in the book, is to plot the same data for the women's lifting, and there was one data point that was unusually high, that didn't fit the trend, and the question asked, what could explain this? And your mind goes to phenomena like strength to weight ratio and the fact that it's women instead of men, and then it turns out that the answer is just that there was a particularly strong but heavy woman that year. Not a, like Brienne of Tarth. Okay, so this is so even in so fleas and elephants one thing, Olympic weightlifters another. This follows quite a fine-grained thing, right? Even within species, this is true. Yep.
Is there a mechanical advantage too? Like if we're just looking at weight class, we kind of lose the info of say limb length. Like a shorter, stockier person the same weight could lift more weight than a taller person.
I don't know. We're getting a little beyond my expertise there. But good question. I don't know. Food for thought. Okay, so how about, why does it take so long for dust to settle? Because the mass is proportional to the volume. So you have a rock, it's going to fall right to the ground. A grain of dust, maybe 10 microns instead of 10 centimeters. It's going to, the force of drag from the air is going to keep it suspended for days perhaps before it settles. This is interesting, scaling in biology. And I don't know if this is quite known why these effects occur, but they're supremely interesting. You know how many times your heart beats in the average lifetime? About 1 billion beats. About if your heart beats once per second for 80 years, that's about 2.5 billion. So 10 to the 9 beats, billion beats. You know how many times a cat's heart beats in its average lifetime? About 1 billion. You know how many times a hamster's heart beats in its lifetime? About 1 billion. So lifespan varies by mass. We're not going to find the Olympic correlation for humans in this particular category, although I don't know if it's ever been looked at. So the lifespan is proportional to the fourth root of the mass, which is proportional to the characteristic dimension to the 3/4, and the heart rate the HR is proportional to the inverse 1/4 root, which is proportional to d to the minus 3/4. The metabolic rate proportional to the mass to the 3/4, which is proportional to the characteristic dimension to the 9/4. Now this could be a point of great hope if we're thinking about nanoscale robots and nanoscale organisms that are going to take over the world. They'll have a very short lifespan. It's also a reason not to kill fruit flies, because they're just going to be dead tomorrow anyway. All right, how does that relate to Tom and Jerry? That's a snooty looking cat. And then this is a particularly pointy mouse. Okay. Again, not to scale. Mass is 5 kilograms of the cat, 50 grams for the mouse. Lifespan is 100 to the 1/4 equals 3.16 to 1. This is the amount of the amount by which the lifespan of the cat is larger than the mouse, and this turns out to be empirically more or less true. The heart rate 1 to the minus 1/4 equals 0.316 to 1, and the metabolic rate 100 to the 3/4 equals 31.6 to 1. Now remember that the heat dissipation of a mouse or a small object in general, even in nanomotor, will be a lot faster. But you'll also have more power per unit volume. So in a way, the strength to weight ratio could be considered a consequence of the higher metabolic rate. Just like you've heard of parents who have their child trapped under a car, can lift the car to free the child, their metabolic rate goes way up, they have this enormous strength. You could think of that continuum as being in effect in the animal kingdom for smaller and smaller animals. Yes?
Question on that. Where do we get 100 for the base of our response? Should move in 500.
Because it's 100 times bigger than the amount?
Because it's the factor by which the, yeah. We're only looking at differences here. Yeah. Okay, now these are all sort of continuum. I think it's a fascinating question to consider whether this is these are real laws or just sort of empirical truths that we have discovered. And something tells me that there must be something quite deep here, that all of these properties are intertwined. And what another consequence of so I should say again that these are all highly continuum theories. So in science and engineering, you have continuum theories and molecular theories. Continuum theories don't rely on any fundamental knowledge of any fundamental structure of the underlying matter. So we don't care about the atoms and we don't care about the molecules. We just consider it as being a block of homogeneous stuff. But as you get smaller and smaller, the atomic and molecular features start to matter more and more. So van der Waals forces become more important. Certainly, the surface area, which is where the van der Waals force acts, can suspend a larger particle than suspend a particle that's large on the basis of its surface area as opposed to something that's large on the basis of its volume, just because it has more surface area. So van der Waals forces are more important for nanoscale objects. In mechanics, the scaling laws tend to be pretty good for even nano-sized objects, but for electronic properties and optical properties, which are highly interrelated, the scaling laws tend to break down. And that was really the topic of the previous nine and a half weeks of the class. But even so, the fact that we have much greater surface areas for small objects has immense practical importance. So for example, if you have a cubic lattice, say cubic crystal lattice, and when you take our crystallography course, you will learn all about the 14 Bravais lattices and what makes them special and the relationships between them. If you consider the total atoms in a nanoparticle and the surface atoms, and you have, say, 13, we'll go backwards, say 13, 55, and 147, chosen at random because these are the numbers that are in the book. So total atoms in a nanoparticle, really small nanoparticles, but nanoparticles that we can actually make in a factory or in a laboratory. So the number of surface atoms for 147 total atoms in a cubic lattice is 93, which is 63%. That's already quite large. So 93 of the 147 total atoms are actually at the surface. But if we shrink this down, 55 total atoms, we have 42 at the surface, which is 76% of the total atoms. But then we have 13, and all but one of the atoms are at the surface. So this is 92%. So while mechanically, even mechanically, this is not going to behave like a bulk structure. So even mechanically, scaling laws break down at these very tiny dimensions. But if you consider the fact that bulk properties are determined by properties of atoms in the bulk, but only one of the atoms are in the bulk, and furthermore, it's not even that far from the surface because it's just right in the middle of this nanoparticle. So it's not even going to have the properties of an atom in the bulk because while it's in contact with one atom in every direction, it's still going to in a bulk structure, it would have much longer range interactions with atoms that are farther away than just the one next to it. So its melting point will be much lower, for example. And its mechanical strength will be much lower because its bulk properties are not satisfied. So as a result of nanostructuring, we can make catalysts that are much more active. So it turns out that because of the high energy of the atoms and molecules at the surface of a structure, which is why we talk about surface energy, it turns out that the reactivity is also much higher at the surface than in the bulk. Because it has unfilled valencies, it wants to grab onto things to lower its surface energy. And when we design a catalyst, say for a chemical manufacturing process, which are almost always nanoscale catalysts, even if they're not nanoparticles, they're often nanoporous systems or surfaces that have a lot of nanoscale asperities on them. So there's a lot of integrated surface area in any efficient catalyst system. You don't want a catalyst system that's a single crystal because if it's a flat single crystal planar structure, then you don't have that high of integrated surface area to react with, right? So nanoscale structures are better catalysts than bulk structures. And for two reasons. One of them is greater adsorption and desorption. So the efficiency, the rate will be a lot higher. And another reason that I already alluded to is greater reactivity of surface atoms. Often not just surface atoms, but also edges, also atomic edges. When crystallographic faces come together, sometimes the atoms at the edge, which are like super surface, because they're like at the tip of a knife, they are especially reactive. Especially edges. So what are some examples of nanoscale structures used ubiquitously? One of them is the Haber-Bosch process. Haber-Bosch process is an artificial process of nitrogen fixation. Artificial meaning that human beings designed it. And unless you eat exclusively organic food, 80% of the nitrogen atoms in your body, as you sit here today, were produced by the Haber-Bosch process, because it's the way in which nitrogen-based fertilizers are manufactured industrially. So that is every third atom in the backbone of a protein, approximately a third of the atoms in all your DNA bases, came from a nanoparticle catalyst that was designed pretty much intentionally as a nanoparticle catalyst to affect this process. Of course, Haber didn't call it nanotechnology at the time, but now that we understand more about nanoscale catalysts, we've actually increased the efficiency of this process a lot. Now, why else is it important? So 80% of the nitrogen atoms in our bodies, in order to produce that much nitrogen fertilizer, it actually takes 1 to 2% of all of the energy used by humanity all over the world. So what is the Haber process? It takes nitrogen gas, just N2, and if we do a balanced chemical equation, which we should always do as having taken our regular chemistry, we have 200 atmospheres. Feels so weird to draw in lowercase letters on this board, but there it is, ATM, always lowercase. Nitrogen plus 3 H2O. And what you have in the typical catalyst is a core iron oxide or magnetite particle, and you have an elemental iron shell. And this is a multi-step procedure, but the temperatures are somewhere between 350 and 500 C, and you get 2 NH3, which can be further converted into non-gaseous compounds like ammonium nitrate, fertilizer, and urea. This is ammonium nitrate. So 80% of nitrogen atoms in your body were fixed by this process. And 4, it has increased agricultural yields around the world by approximately a factor of 4. And it costs 1 to 2% of world energy supplies. And at the core of all of it, pun intended, it's a iron oxide magnetite nanoparticle with an iron shell. You can use other catalysts as well, but this is the most popular one these days. Another example is another type of reduction reaction over a metal catalyst precursor is hydrogenation. Where you have some, it could be any unsaturated or any any oxidized compounds, but in particular, I'm going to talk about where we take a carbon-carbon double bond and we have a metal catalyst, and the metal could be platinum, palladium, or nickel, which all have similar reactivity because they're in the same group of the periodic table. And what you do is you just reduce this double bond to a single bond by adding the hydrogen atoms across it. So it looks something like this. You have a surface where you have adsorption of the substrate. Absorption of the substrate and dissociation of H2, or dissociation. Some of you will go on to careers where you have to do a lot of public speaking, like teaching, and you will second guess your spelling of quite common words because you have 80 people staring at you. But I think I got that right. And the second step, we have one hydrogen atom adds. So the hydrogen atoms add one at a time. And then finally, we have both hydrogen atoms add. And this is fully hydrogenated or hydrogenated. Depends on which syllable we want to emphasize. And desorption. We can imagine that I've drawn a flat surface here, but if we had a porous surface, which is how this is normally done, that we would have a much greater rate of desorption and of more and more moles, say, of the substrate per minute. Yep.
It definitely seems like catalysis is a really important part of nanoengineering. But is there a course that kind of talks about the mechanisms of catalysis and what a catalyst actually does in a reaction? That's
a good question. The best place, so the question was, given the importance of catalysis in nanoengineering, is there a course you can take? The best course is an organometallics course. Okay. If you take, sometimes that's offered as a graduate elective in a chemistry curriculum, but it will assume some knowledge of inorganic chemistry. By inorganic chemistry, I don't mean general chemistry, which is kind of like baby physical chemistry. Inorganic chemistry is about space groups and the Jahn-Teller effect and ligand environments and inorganic spheres, and it's mostly homogeneous. So in catalysis, I'm glad you brought this up. So catalysts come in two flavors, homogeneous, that is dissolved in solution, and you have heterogeneous, which is two phases. Two-phase systems. Heterogeneous catalysis is used much more this is like what I've been talking about is primarily heterogeneous catalysis. It's by far more important industrially in the production of commodity chemicals and even non-commodity chemicals, but you do it in large batch reactions. You generate stuff on the hundreds or thousands of tons at a time. So this is let's say this is important industrially. Industrial, let's say commodity. And I mean commodity materials, commodity chemicals. Not always. You can make specialty and engineering materials using heterogeneous catalysis, of course, and it's done all the time. But I mean to differentiate that from homogeneous catalysts, which are usually used for fine chemicals, research. The catalysts themselves, so research, this could be, so what do I mean by fine chemicals? By fine chemicals, I mean pharmaceuticals, I mean engineering plastics sometimes. Now, again, these are not hard and fast rules. This is just where you're more likely to find these catalyst systems. What you also have in homogeneous catalysts, a homogeneous catalyst is a molecule. So homogeneous, these are molecular. These heterogeneous catalysts are nanoparticles or surfaces, or nanostructured surfaces. Molecular catalysts are more difficult to recover. And why? Because they're in the solution. Heterogeneous catalysts are easy to recycle. Sometimes just by filtration. Sometimes you can filter the particles off in literally a filter, and then wash them and reuse them. Or or say in the case of the Haber-Bosch process, there are particles that are in some giant multi-layered sheet of in some reactor, and the substrates move through them, the nitrogen moves through them, the hydrogen moves through them, and then you regenerate the catalyst through some process if it gets fouled or poisoned along the way. Homogeneous catalysts, a lot of times in a research lab, once you're done with these, you just throw them away, unless they're attached to a bead or something, in which case you get sort of the best of both worlds. You get something that's bound to to a plastic microparticle, but it's a molecular catalyst. So that can be done as well. I'm really glad you brought that up because that's an important point. This also includes enzymes. So oftentimes in chemical processes, enzymes are used. They're isolated from some biological source, and then they're used in a chemical manufacturing process. Yep.
The naming seems almost counterintuitive because it seems like you're describing homogeneous things you gave the example of enzymes, whereas heterogeneous, I'm imagining, heterogeneous sounds like a mix of different things, but you mean like silver particles that are used to catalyze some organic reaction. Do we call those heterogeneous?
So the idea is that the question is, what is the distinction between homogeneous and heterogeneous? Because it seems like a little bit of a contradiction. A homogeneous solution is a liquid. Everything about it is a liquid. You can't filter it through any reasonably sized, a few micron pore filter, and you'll get the same exact solution out the other end. In a heterogeneous system, you have solid particles that could be nanoparticles or a surface or a mesoporous surface, for example. This process of hydrogenation, and this is just in case you haven't seen this kind of thing before, sometimes this doesn't go to completion, and sometimes the bond instead of this bond breaking, it flips. So sometimes you go from this bond to a bond where the carbon atom over here is flipped. Now, in this case, it doesn't matter because you have the same thing, which is just a stick on either side. But suppose you said that this was A and this was A. But then if you flip these, then A is up here. So in that case, we have to make the distinction between cis double bonds and trans double bonds. And this just is the last bit of new information I'll leave you with in the entire course. This is a cis unsaturated fatty acid. And this is by far the more common one in biological systems. And cis unsaturated fatty acid can't pack very well in a solid because of this kink in the chain. So the cis unsaturated fatty acid is usually more likely to be a liquid because of poor packing. And then the opposite one, and I'm not going to make any effort to draw exactly the same number of bonds. You can, for homework, draw the same number of bonds. This one is a trans fatty acid. Ooh. Which are the opposite of everything I wrote here and also make Dunkin' Donuts delicious. A saturated fatty acid has no double bond, and it forms the most solid material of anything. So you take olive oil and you hydrogenate it, you'll get olive oil margarine. And if you don't hydrogenate it to completion, which is sometimes done intentionally to make it more of a semi-solid or to make the donut glaze stick better to the donuts, then you use the trans fatty acid, which is now illegal in some municipalities. Thank you very much. I'll see you on Friday.